So, welcome to this lecture. Today, we are going to discuss a new kind of interpolation method, and that method is going to discuss the problems in which arguments are unequally spaced. If you remember, so far we have discussed the problem of the interpolation methods, maybe the Newton's forward interpolation problem, or Newton's backward interpolation formula, backward interpolation problem. In all cases, the arguments were equally spaced. And this assumption was very much laid down while discussing the interpolation methods. And that was very popularly known as a width or length of spacing or interval or difference. Now, today we are going to discuss such a problem, such a method, which involves unequal space. If everything is, I mean to say, the arguments are equally spaced, then we have lot of methods so far which can apply over there to compute the value of the function. The value of the function was decided according to the location of arguments and values of the function, that may be beginning, that may be end. Now, this kind of process is going to be over, and we have entered into another kind of discussion which allows us to have the interspacing unequal. And that very method, which we are going to discuss for unequal spacing, when arguments are spaced unequally in the means, if you remember earlier, the arguments were arranged or put like what? Arguments were put like 1, 2, 3, 4, 5, or 2, 4, 6, 8, so forth, so on. Means this distance was equally spaced. Now we are going to discuss in such a way that these arguments are not equally spaced. How are these arguments? Now arguments may be spaced like 1, 3, 5, 7, 11. So there is no any set and understood pattern or any uniform pattern which can guess that the next argument will be this. When we understand the space, there is no problem of assessment of the next value of the argument. But now today we are going to discuss the Lagrange method of interpolation, which allows this special advantage or a special facility of computation. This special facility of computation is popularly known as interpolation with unequal intervals. As we know that, if you look at here, this interpolation with unequal intervals, this one, here everything was equal. Now this is one letter is left unequal. Everything was equal, and I think these Newton's forward and Newton's backward interpolation formulae were very popular, were very famous to apply to compute the values of the function corresponding to the values of the arguments in the given range. Now we are going to discuss today another method which is popularly known as Lagrange formula for unequal interval. This is Lagrange formula. This is not Lagrange formula. Is it okay? So we have to correct our pronunciation also. The name of the mathematicians we must try to pronounce perfectly, not perfectly, almost near to perfect, or we should try to understand. So Lagrange formula, not Lagrange formula. So what does Lagrange formula says? As usual, let y is equal to fx be a real valued function. What is the real valued function? Real valued function is a function which provides the value on the line of real system. And the domain is real and codomain is also real, which is continuous in the interval AB. We can assume any interval, but at this point of the time, now under this interval, all these values are lying. We have to keep in mind that literature does not specify that why we have chosen the AB, but here we have to keep in mind, we have to be, we have worth mentioning here, we have to worth mentioning here that these intervals, these values are within this interval and which are not equally spaced. You look at here. Earlier the assumption was very strict assumption in case of the Newton's forward interpolation formula and Newton's backward interpolation formula. This condition was very restrictive, very strict, that this was equally spaced. Now it is not equally spaced in the contradiction of equally spaced. So corresponding to values of function are denoted as usual y0, y1, y2, yn, so forth. So on yn, thus we have n plus 1 data set as usual. There is no any problem here. But in this very case, let us discuss uh, the problem of representation of the polynomial through any polynomial. So as usual, we have decided here to denote phi x by a polynomial, be a polynomial of degree n. How many data set? We have data set n plus 1. Therefore, degree is what? Degree is n. Means polynomial will have the degree n, and this is responsible for representing the actual function y is equal to fx. Okay. So it is a polynomial, it is a function which is being represented by this polynomial phi x. So we are just designing and devising this formula for the polynomial. And why we are designing or devising this kind of formula, you have known earlier also. What is the purpose? Purpose is just to have the derivation and interpretation of the formula given by the Lagranges. And in this very case, we need such a kind of design or beginning formula so that we can have the derivation. But in general, the character of that formula or that polynomial should not violate any generality of the mathematical concept, means character of the mathematical concept. So this first term you look, the first term you can look here. We have started from a naught as usual, the coefficient x minus x1, x minus x2, so forth, so on, x minus xn. So when you multiply, one x is here, another x is here. So how many x we have? We have x n times. So if you multiply Each term has n factors. Each term of this polynomial has n factors, and if you look at here, what will be the degree of this term? Degree will be n. Similarly, we have also another term x minus x naught. When here is a naught, then here is no x naught, because ultimately we have to compute the value of a naught. And if you put here x is equal to x naught and x, when we again assume that x is equal to x naught, so x naught minus x naught is equal to 0, and this term becomes 0. And therefore, you look here cleverly as a mathematical clever, clever is there. Uh, what, how we just to here manipulate x minus x naught. Here is a1. So a1 is not, x1 is not here. X minus x naught, x minus x2, so forth, so on, x minus x1. So if a1 is here, then x1 we won't find. This is our cleverness. This is our mathematical cleverness, we can say, or mathematical intelligence. By that we are devising and designing this very polynomial. Now A2, if we look at here A2, x minus x naught, so x2 is not here. X2 is not here means x3 is here, you look at. You look at here, x1 is here, x naught is here, xn is here, but you won't find x2. Similarly, the last term I am showing you for your curiosity that an is here. So you won't find what? Xn. You won't. You look at here. The whole factors, all factors of the whole term, you won't find the xn. So this is the way, the clever way of designing this polynomial, and always we have presented before you different polynomials which are responsible to represent and try to actualize the function in the beginning, y is equal to fx. So this is also another kind of polynomial, but character is well defined. Okay, it is this. There is one note here. Each term in A has n terms, means each n factors, not term. Each term has n factors of degree n. We have already discussed this very point. Okay, let us come to next point. Next point is what? The similar procedure as we have done in almost all derivations, all interpretations of interpolation methods. X assume letting x is equal to x naught in A. When x is equal to x naught in A, what does it mean? We easily get in the same way. Y x naught is left hand side. A naught, I told you, it has no any x naught. So this, only this term containing these factors will remain. Other, wherever x naught in the right hand side means here is x naught. Almost in all terms, very exactly in all terms that involves the x naught, that x naught enters into all terms, and therefore each and every terms become 0. Only remaining is this part, and this is what? This is representing the function, primary function chosen. So this is nothing but it is representing the y naught. So y naught is here as usual here, and then y naught, sorry, a naught is computed in this way. So this was the purpose. Designing of the special polynomial was only to compute and determine the value of a naught. And this kind of things in the numerical analysis, this is a repetitive process or iterative process in several methods. Okay, in the similar way, by putting by use of x is equal to x naught, x is equal to x2, sorry, x1, and then x is equal to x2, so forth, so on. The x is equal to xn in A, but here there is one term left. You can correct it for yourself respectively. It is respectively. It is respectively. Means x is equal to x1, then x is equal to x2, then x is equal to xn. So by doing this we get the value of a1. When we get the value of a1, what will happen? Value of an, so forth, so on. All values are computed here, and therefore now we have this thing, phi x. Substituting the values of a1, a2, an in a, we have this one. Phi x is equal to, substitute, a1, a naught is replaced, a1 is replaced, a2 is replaced, a3 is replaced, so forth, so on. An is replaced. So plus plus plus, and this is y1, this is last. So here is also, here is, so forth, so on. Means similarly there are several values in between this we have to write here. So this is known as Lagrange interpolation formula. This formula is very useful. So remember this formula. This is very easy. It is free from any beginning value, any ending value. It is unequally spaced. I mean, arguments are unequally spaced. In this way, this has more flexibility than previous method. It is here. It is not end of any, I mean, excitement. We have more excitement regarding the Lagrange interpolation formula, and this kind of attraction, this kind of excitement you so far never found in any method. What is this excitement? This study of excitement, that is a point for inverse interpolation. In no any method you have seen that for given value of y, you compute the value of x. It is very interesting. It is a double-edged sword. It is a double-edged sword. You can use the sword either way. दो तरफ से ये अच्छी सी तलवार है जिसमें दोनों तरफ धार है, चाहे सीधा चलाओ चाहे उल्टा चलाओ. So this kind of facility was never embedded, never endowed with any previous method. So it has the special advantage of having the two things. One is the facility of interpolation, computation of the interpolation, and another facility is the inverse interpolation. Inverse interpolation, we can inverse the process. Inverse the process means we can find the value of x for corresponding value of y. This is a special thing which we are going to discuss today. So it has twofold advantage. We have seen it has twofold advantage, inverse. So the value of argument x corresponding to the value of function y means we have to give the value of y and we need to compute the value of x. It is very interesting. In this way, it has twofold advantages. What advantages? One is the interpolation as usual in other methods, and the another property or facility which it allows to be endowed with is the estimation for tabulated data set, means value of y. So Lagrange interpolation formula we have so far known as Lagrange interpolation formula, and that Lagrange interpolation formula, as usual, remember this formula x naught. We start with x naught here. X naught is here, x1, x naught minus x2, x naught minus x1. The first term always come to the denominator immediately, and then how you will set the numerator. If it is x naught, then we will start subtracting from x1. We leave out the x naught, then x minus x2, so forth, so on, x minus x1. So first you set your denominator that it is going to start from x naught. Immediately you will start the subtraction from x1. And then here is y naught. Y naught is corresponding value of x naught. Second term, how we set the second term? Second term immediately come to the numerator, sorry, denominator, and denominator starts begin with the x1, x1 minus x naught, x1 minus x2, because x1 minus x1 is not allowed, x1 minus xn, so forth, so on, and corresponding to x1, here you have to put the y1. And x1, if it is x1 here, so it will not start, numerator will not start with the x1. So it was started from x1 because here was the x naught. So in this way, here is x1. So beginning value of x is what? X naught. So we will start from x naught. We will start from then x1. We will subtract xn from x. So this kind of formula you need to remember by setting your pattern of the formula. Otherwise, there is a chance to commit the error while writing the formula, while putting and substituting the values. And you look at here, the last term is where denominator, this is xn, this is xn, this look like xn, so this is xn, xn minus x naught, xn minus x1, xn minus xn minus xn minus, and then here is xn, so xn won't be subtracted, xn won't be here, so here is what we started from x naught, the x1 and the x minus, and the last is y. This is the last value of y. So in this way, this is the a is Lagrange interpolation formula. Now, if we interchange x and y in A, we get argument x as a function of y. When this is function of what? You look at here, this is function of x. But here, this is function of x, means this is y. This is y. But here, y won't be here because we are going to interchange. So if we are going to interchange, x will be y, and just here, look at here, I won't write here. If this, you say this will be function of, this will be function of y. If it is function of y, if it is a function of y, so what we will get? We will get x. Now, we will get. So this kind of procedure is going to take place, transpire here, and therefore you just see, here is x, here is x, here is x, and here is y, y minus y1, y minus y2, similar fashion, similar manner as I told you to set the pattern. Here is y naught, so you will start from y1, y2, so forth, so on. Here is y naught, then you will substitute, put here, you look at here, the change, it has been changed. Earlier this was y naught. Similarly, you come to the downside, denominator, you set here y1 minus this, y1, y1, y1. So y1 is here, so you will start from y naught, y2, and y1 is not here. Similarly, yn, every value subtracted from yn, you look at here. So this yn means yn would not be here. So here is no yn minus 1, but you won't find, you won't find this yn. So in this way, this is a formula B, and this formula B is popularly known as inverse interpolation formula given by Lagrange. So this is Lagrange's um, contribution is enormous. It is remember worthy and worth remembering for us as a student, as a teachers. And therefore now the concept is only possible when we demonstrate the numericals or applications, and we will do the numerical applications. I mean, next term there will be two important numerical applications. One for the Lagrange direct method. Direct means without inverse, and another is Lagrange inverse interpolation formula. So just to summarize, today we discussed the interpolation method for the function whose arguments values are not equally spaced. So that is known as a unequal interval. So in very short, interpolation, we call it, we say it, interpolation with unequal intervals. So it has two advantages. One, as usual, the interpolation of the function for given values of x, and another advantage it has, that is the advantage of inverse interpolation, that is inversing the process of interpolation. Inversing the process of interpolation means now we are going to compute the value of the argument for given values of function. This is very important. And if you remember, thus any situation in your any course or any papers, recommended papers, prescribed papers, you won't find this kind of thing. You have studied the regression analysis, two lines of regression. Not single line can allow you to compute the value. If you are computing the value of y, the line of regression of y on x, then you cannot compute the value of x for same line of regression. So if you want to compute the value of x, then you have to derive and design the line of regression of x on y. The same line of regression of y on x cannot be used for reverse computation. The reason was we minimize the error in designing that regression line. Means we minimize the errors of computations, errors of observations, or errors of measurement. As I told you already, that whenever any machine, whenever any individual is going to measure, is going to observe, is going to compute, is going to estimate, is going to approximate, the error has to happen. Error must happen. Nobody can stop this very process of, this is a natural thing. And therefore we have the limited powers, limited facility of our senses, and therefore this kind of things will happen. So this is, we have seen a special advantage. So next turn means tomorrow we are going to discuss, this very formula, application, and after this application, the difference, backward, forward, unequal intervals, this kind of one procedure will be closed, and then we will be able to discuss the central difference. Still we have not discussed the central difference. So in your course, if you remember, you look at your outline of your course, you will find there is one term there, and somebody was asking me, sir, what you are teaching now, is it in your course or not? There it is simply written interpolation. It is interpolation. You can't leave all these things because these courses are recommended for various competitive examinations. For MSc is the foundation course. You cannot overlook the courses day today or tomorrow. If you join somewhere as a teacher, as a faculty member, as an officer, as a competitive candidate in your UG, CNET, each and everything, then separately you need to get the coaching. Reason is that we are not equipped with the basic concepts, and therefore when we start anything, there is no hurry. If there is a hurry, I will finish the course. If you will say within a week I'll finish the teaching, I have no problem. But unless you have the basics, so we started with the interpolation and we will finish with the central difference. Then and only then we can say now the interpolation is going to complete. So from that point of view, if you have any questions, then we can go for this question. And